Hi boys and girls, in the last class, last video, you have learned about basic gates like the AND gate or the conjunction, the OR gate, the disjunction, the inverter, the negation, and variations of that like NAND, NOR, etc. Now in this video, we will see about some basic laws of Boolean algebra. They are called De Morgan's laws and XOR gates. Okay, so let me start with that presentation. So this topic is De Morgan's laws and XOR gates. So this speech is organized into your learning outcomes, then the De Morgan's laws, the exclusive OR gate, the exclusive NOR gate, and your learning outcomes, what you learned at the end. So in this video you will learn the De Morgan's laws, which is central to Boolean algebra. Then you will learn the exclusive OR and exclusive NOR operations and gates with the truth table, and verify their operations and verify the truth tables with the cubes. Now the Boolean algebra says the De Morgan's law says A or B all complement that is equal to A complement O and B complement. The first line says A or B all complement, that is one of the De Morgan's law, that is A or B all complement that is equal to A complement and B complement. What is the meaning of this A or B complement? എയോ ബിയോ അല്ല. ഓക്കെ, മലയാളത്തിൽ പറഞ്ഞാൽ എയോ ബിയോ അല്ല. അതിൻ്റെ അർത്ഥം എന്താണ്? എ അല്ലായിരിക്കുകയും ബി അല്ലായിരിക്കുകയും ചെയ്യുക. ഓക്കെ, എ അല്ലായിരിക്കുകയും ബി അല്ലായിരിക്കുകയും ചെയ്യുക. അത് ദാറ്റ് ഈസ് ഈക്വൽ ടു എന്താണ്? എയോ ബിയോ അല്ല. Then that is the first thing. A or B all complement that is equal to A complement and B complement. Now what is AB complement? എയും ബിയും അല്ല. ഓക്കെ, എയും ബിയും അല്ല. അതെന്താണ്? എ അല്ലാതിരിക്കുകയോ ബി അല്ലാതിരിക്കുകയോ. ഓക്കെ, that is what is that in mathematical terms? What is that? A B all complement that is equal to A complement or B complement. Okay, so these laws are central to our studies. So A or B all complement that is equal to A complement and B complement. What is the meaning of that? എയോ ബിയോ അല്ല എന്ന് പറഞ്ഞാൽ അതിൻ്റെ അർത്ഥം എന്താണ്? എ അല്ലാതിരിക്കുകയും ബി അല്ലാതിരിക്കുകയും ഉള്ള അവസ്ഥ. ഓക്കെ, അതാണ് ആൻഡ് ഓഫ് വാട്ട് കോംപ്ലിമെൻറ്റ്സ്. നൗ എ ബി ഓൾ കോംപ്ലിമെൻറ്റ്, എയും ബിയും അല്ല. വാട്ട് ഇസ് ദാറ്റ്? എ ഓർ ബി എ കോംപ്ലിമെൻറ്റ്, എ ബി ഓൾ കോംപ്ലിമെൻറ്റ് ദാറ്റ് ഇസ് ഈക്വൽ ടു എ കോംപ്ലിമെൻറ്റ് ഓർ ബി കോംപ്ലിമെൻറ്റ്. വാട്ട് ഈസ് എ ബി ഓൾ കോംപ്ലിമെൻറ്റ്? ദാറ്റ് ഈസ് എയും ബിയും അല്ല എന്നാണ് അതിൻ്റെ അർത്ഥം. വാട്ട് ഈസ് ദാറ്റ്? എ അല്ലാതിരിക്കുകയോ ബി അല്ലാതിരിക്കുകയോ ചെയ്യുന്ന അവസ്ഥ, അതാണ് എ ബി ഓൾ കോംപ്ലിമെൻ്റ് എന്ന് പറയുന്നത്. ഓക്കെ, നൗ we will see some simple formula, simple derivation from these two laws, like A or A complement that is always a 1. Okay, because if A is 1 it is 1 or 0, that's a 1. If A is a 0, 0 or 1, that's a 1. Okay, A and A complement is 0, because if A is 1, A and A complement A is 0. If A is 0, it is again 0. 1 or A is always 1, because if A is 1 or 0, irrespective of A is 1 or 0, 1 or A is a 1. And 1 and A is A, and 0 or A is A, 0 and A is 0. A or A complement B is nothing but A or B. A or A complement B, that is equal to A or B. That is the 9th theorem. A or A complement is 1. That's already I discussed. I think that's a repetition. A or A is A. There is nothing like a 2A. A or A is it is A. A and A is again A. Check with A equal to 0 and 1. Now there is a derived gate that is called the exclusive OR gate, that is derived from AND OR functions. That consider the function A equal to A exclusive OR B. This O plus sign that is used for denoting the exclusive OR operation, that is A exclusive OR, which is nothing but A or B and A complement or B complement, which is nothing but AB complement plus A complement and B, A and B complement or A complement and B. Okay. Now this its truth is dependent on truth of the exclusive OR gate, that is dependent on the parity of the input bit applied to the gate. Parity is nothing but the number of bits in a binary, number of ones in a binary word. Like if the binary word is 1 0, if there's only 1 1 in it, so the parity is a 1. Now, if I have a word called 1111, its parity is 4. If I have a word 1110, its parity is 3. Parity is the number of ones in a binary word. Now, this exclusive OR function is true when the input word has an odd parity and false when the input parity is even. That is, the number of ones in it, the input word is odd, then its output is high. Or else, if parity is even, if it is odd parity, then the output is 0. So, the schematic is shown here. That is, if AB if this word AB has a odd parity, like if it is a 0 1 or 1 0, then the output is a high. If it is a 1 1 means parity is even. 0 0 again parity is 0, which is a even. So then in those cases the output is a 0. So if I look at the truth table of the exclusive OR gate, it is 0 0 it is 0, 0 1 it is 1, 1 0 it is 1. Why? Because in these two cases the parity is odd. If you look at the word AB, the parity is odd. So the number of ones in it, this is 1, here it is 1. So this is odd. That means output of the exclusive OR gate is 1. In the last case and the first case, the parity is even. Here I have 0 1, so that is an even number. 1 1, it is again the parity is 2. So this exclusive OR output is a 0. Now, a complement of that is, I cannot say it's a complement. It depends on the parity again. I should not say exclusive NOR is a complement of exclusive OR. The XNOR function that looks like y equal to A and B, or A complement and B complement. The earlier case, exclusive OR, it is A and B complement, or A complement and B complement. Here it is slightly different. It is y is A and B, or A complement and B complement. The schematic looks like this with an inversion at the end. In the case of a two input case, that inversion is correct, but not always. Okay. If the input word is contains odd bit, like 3-bit or 5-bit, then the exclusive and the exclusive NOR outputs are same. But if they are 2 input, like 2 input or 4 input, then the exclusive NOR is a complement of the exclusive OR. Exclusive NOR operation is not always a complement of exclusive OR operation. If it is a 3-bit case, if it is a 3 input exclusive OR gate, that's the same as a 3 input exclusive NOR gate. But a 2 input exclusive operation is a complement of the 2 input exclusive NOR. So never say that exclusive OR is the complement of exclusive NOR. NAND is a complement of AND, but exclusive NOR is not the complement of exclusive OR. It gets complemented only when the input bit is even. Input bit pattern is even numbered. Like if it is a 2 input XOR, the XOR and XNOR are complements. But if it is a 3 input gate, like if it is a 3 input XOR function, then the XOR function and XNOR function are the same. So this is the schematic of the exclusive NOR function, and the truth table looks like this. If the word has, what is the truth of this function? Truth of the function says that if the input word has even parity, the output is a 1. If it has got odd parity, the output is a 0. So if it is a 0 0, if it is a 0 0 and 1 1, the output is a 1. For 1 0 and 0 1, the output is a 0. So here it looks like the complement of XOR, because it's a 2 input case. For a 2 input XOR is a complement of 2 input XOR. But a 3 input XOR is the same as the 3 input XOR. A 3 input XOR is the same as the 3 input XOR. This you should not confuse. So before I go to this exclusive OR and exclusive, before I close down, I will show you how I can verify this truth table. This you can verify in the board by using the 7486 IC. Okay, in the previous thing I have shown that. Now I will show you how I can do a QX to verify this. So I will go here, I will take a QX thing. XOR is here, there's an XOR.sh. If I take here, you can see that this is an exclusive OR gate with 0 propagation delay, and voltage level 1, and this switch has 1 nanosecond, sorry, this source has 1 nanosecond with starting low. This switch, this source has low and low and high for 2 nanosecond. Now this digital simulation, that is a time list with a Verilog model. Now I run this simulation. Let me run this simulation. You can see that you can see this timing diagram. You can see that I will drop the tabular also. First I will look at this thing. So if one of this is 0, then the output is a 0. Here B is 0, A is 1, so this 1 0. Here it is 1 1, so the output goes low. Here again it is a 0 0. Again the inputs are the same, so the output comes here. Okay. Here again this is a 0 1 pattern. Again this goes high. This is a 1 1 0 pattern. Again it remains high. Here it is again a 1 1, so it goes low. It's a 0 0. Again it goes low. This is the way my waveform behaves. And let me look at a tabular type thing that will corroborate your truth table. You can see that 0 0. You can see that in the truth table it is a if you look at the truth table, when the input bits are 1 1 1, that's a 0. Again 0 0, it is a 1 0 1, it is a 1 1 0, it's a 1 1 1, it goes to a 0. So if the this is an exclusive OR operation. So let me close this window. Now you have to look at an XNOR thing. XNOR will be an inverted output. Okay, here I will run a simulation. Here you can see the effect. You can see that when the two are equal, that is when it is 0 0, the output is a 1. When it is a 1 0 or 0 1, the output is a low. When both bits are 1s, again the output is low, high. Here it is both bits are 0, that is they are equal, so again it is high. When these two bits are different, they again remains low. Here it is 1 0 0 1. Here it is 1 1, so it gets a high, and here it is a 0 0, again it remains at a high. And if you look at the truth table, you can see so that this is a 0 0, it's a 1, 0 1, it's a 1, 1 0, it's a 0, 1 1, it's a 1. Okay, so this is how the explosive NOR behaves. This is the truth table of the explosive NOR. So one thing I want you to note specially is that you should not, the NAND is the complement of AND. NOR is a complement of OR, but never say that explosive NOR is a complement of explosive OR. Only if it is a 2-bit or 4-bit, the explosive OR and explosive NOR are complements. If it is a 3-bit gate, if it is a 3-input gate, explosive NOR and explosive OR are the same. So what you understood in this video is that you understood the De Morgan's laws, then you understood the operation and truth tables of explosive OR and explosive NOR gates. This you can verify with 7486 IC. Then you verified the truth tables of all these gates with cubes. And that's the end of this session. I thank you all.